Alright, number one, changing to logarithmic form. Simply going to be log base 2 of 16 equals 4. The bases are 2's. What was by itself becomes the argument, and the exponent becomes something that's by itself. Number two, you're going to get log base 3 of 1/27 equals negative 3. Bases are the same. What was by itself becomes the argument. What was the exponent goes by itself. Number three, we got log base 8 of 1/4 equals negative 2/3. Base is the base. What was by itself becomes the argument. What was the exponent becomes by itself. 4, 5, and 6, write the equation in exponential form. So what we just did, but backwards. Base is 2, exponent's 3, equals the argument, which is 8. Notice once again the bases are the same. What was by itself is the exponent. What was the argument goes by itself. Same thing with number 5. Base is the base. What was by itself is the exponent. What was the argument is by itself. Number 6, base is the base. What was by itself is the exponent. What was the argument is by itself. Number 7, evaluate each expression using a log identity and number 1. Since this log has a base of 9 and the argument has a base of 9, the answer is just the exponent, 6. Number 8 and 9 are the same thing. Well, very similar. Number 8 is log identity number 2, I believe. You have a base of 12 that has an exponent, and that exponent also has a base of 12. So that just equals the argument of the exponent, which is 5. Number 9 is the same as number 7. Log ID number 1. The base of the logarithm and the base of the argument are the same, therefore the answer is the exponent. Number 10, 11, and 12, same directions. Number 10, log ID number 1. Same base for the argument as the logarithm, so the answer is the exponent, which is 10. Number 11, same problem again. There's no exponent there for the argument, therefore the exponent is 1. Number 12 is not as simple. This one is a little bit more work. We would like to say the answer is just 2 because the exponent and the base are the same number of 10. Scratch that. The base of 10 is the same as the base of the exponents of the logarithm, both 10. So it'd be great if the answer was just 2, but it's not because that 4 is hanging out in front. That 4 needs moved. Notice the 4 was the coefficient of the exponent, and now it's the exponent of the argument in the exponent. That's the power rule. 2 to the 4th is 2 times 2 times 2 times 2, which is 16. At this point, we can use a log ID number 2, which makes this 16. (13) and 14 solve the equation. Our goal, in most cases, is to take the argument, which is 0.04, and write it in such a way that it has the same base as the logarithm's base. So, to examine this further, we'll take 0.04, which is read 4/100ths, and write it as a fraction. The fraction would be 4 over 100. 4 over 100 reduces to 1/25. So how can we write 1 divided by 25 as a base of 5? We want a base of 5 because our logarithm has a base of 5. We can simply write it as 5 to the negative 2. 5 squared is 25. Since the exponent is negative, it's going to reciprocate that 25 and get 1/25. Log identity number 1 therefore says this is just the exponent of negative 2. Number 14. Using the property of equality. The left side of the equation and the right side are both written in one logarithm. They both have the same base. Therefore, the argument on the left is equal to the argument on the right. Divide both sides by 3 and you get x is 12. Number 15. We would like the 216 to be written as a 6 to an exponent. We can do that because it's the same as 6 to the third. Log ID number 1 says that is just going to be the exponent, which is 3. Number 16, we have a sum on the left. We would like to get this to a point where it's just a log equals a log. To get rid of the sum on the left, we can use the product rule, which says if you are adding two logarithms with the same base, you can multiply their arguments and just write the logarithm once. 4 times 6, of course, is 24. Once the left and the right only have one logarithm and they have the same base, simply set your arguments equal to each other. X is by itself, so x is 24. 17, we have subtraction. Log base 3 of 12 minus log base 3 of x can be written as log base 3 of 12 divided by x. When subtracting logarithms with the same base, you can write it as a quotient or fraction. Property of equality therefore states that 12 divided by x equals 3. Multiply both sides by x, then divide both sides by 3. You get x is 4. 18. We have a sum again. To make that a product, multiply the arguments. Using brackets around, since each of the things that I'm multiplying is in parentheses, you're going to use brackets to emphasize that the logarithm applies to everything in the brackets. If you simplify that, x minus 3 times the difference of x plus 3, you're going to get x squared minus 9. If you then take this, what we would try to do on previous problems is write the x squared minus 9 as a base of 4 with an exponent. That's not possible for us to do. So if we use the definition of logarithm and change this to exponential form, this will be 4 squared equals x squared minus 9. We no longer have to worry about logarithms, and we don't have any variables in the exponents. So you would just solve this like you would solve an equation before you learn logarithms. 4 squared is 16. If you add 9 to both sides, you get 25 as x squared. Square root both sides, you get plus or minus 25. Got to be careful with some of these answers. Your argument is not allowed to be negative. So let's check. If we were to put a 5 into the arguments, we would get positive answers for sure. If you put a negative 5 in, let's see what would happen. Let's just focus on the beginning of our logarithm. The log base 4 of x minus 3. If you put the negative 5 in for x, you're going to end up with log base 4 of negative 8. Your argument must be positive. Since it's negative in this case, that means negative 5 is really not one of our answers. Our answer is only positive 5. Number 19. On the right side of the equation, we are adding two logarithms with the same base. Therefore, we can multiply their arguments. It's the product rule. The argument on the right can be simplified as 6x minus 12. Using the power property, we can take 5x and set it equal to 6x minus 12. Solving the equation, we're going to get x is positive 12. Number 20, graph the equation of inequality. If you know what the parent graph looks like, and you should, you know there's a vertical asymptote at the y-axis, which is x equals 0. Also, this logarithm has no numbers that you're adding or subtracting or any place. You're not multiplying by any numbers as coefficients. You're not dividing by anything. This has the same shape as the parent graph, and it's the same location. It crosses the x-axis at 1. Recall that the bigger your base is, the faster this goes to the right. So if the base was 10, it might come real close to the x-axis. If the base is 1/2, it might go real high before it starts going to the right. Number 21, a log base 1/2 of x. Notice in 20, the shape. And this one here, it's the same shape, but it's just going to go a little bit higher. We have the vertical asymptote, same place because we're not adding or subtracting any numbers. There's no translating. This graph's going to go a little bit higher before it goes to the right. It's still going to cross at 1. It's going higher because the base is a smaller number. 22, similar to 20 and 21, has a base of 6, so it's going to be tighter to the x-axis. Also, it says less than or equal to, so we're going to shade below the curve, still crossing at x equals 1.